For integers a and b with a different than 0, we say that a divides b, denoted by this notation here, so it's like a vertical bar here, division, if there exists an integer k such that b is equal to a times k. So, for example, 3 divides 15 since 15 is equal to 3 times 5. So in this case, our integer k that exists is the integer 5. So there exists a number that when you multiply by 3 gives you 15, right? And that number is the number 5. And of course, it has to be an integer. It can't be a fraction or anything else. So we're only talking about integers here. Another example, so 4 divides 28. Why? Since 28 is equal to 4 times 7. So once again, exists an integer, the integer 7, that when you multiply by 4 gives you 28. And let's see a non-example. So 5 does not, and you can write this in many ways, does not divide 12 since there is no integer. There is no integer k such that 12 is equal to 5 times k. So since there doesn't exist any number that when you multiply by 5, any integer that when you multiply by 5 gives you 12, that means 5 does not divide 12. So let's see some of the basic divisibility properties. So suppose that a, b, and c are integers, then for every a different than 0, we're going to have that a has to divide 0. So let's see these properties and see why. So since 0 is equal to a times 0 for every a, that means that for 0, there always is going to exist an integer k, in this case 0, such that a times 0 is equal to 0. So this implies that a divides 0. Also, since you can always write a equal to a times 1, then again, there is always going to exist an integer. For every a, there's going to exist an integer, the integer 1, such that when you multiply a by 1, you get a. And so this just means that a divides a. And also, for every integer b, you can always write, how do you say, b in the form 1 times b. So now it looks the same as this, but we sort of swap the order here. So now our k here is going to be b. And what we mean by this is that there's always going to be an integer b that when you multiply by 1 gives you your b. And so this implies that 1 divides b. And so these are always going to be the case. A divides 0, a divides a, and 1 divides b for every integers a, b, and c. For the second one, if a divides b and b divides c, then a divides c. So how do we show something like that? So since a divides b and b divides c, that means that there exists integers k and l, so k and l integers, such that b is equal to ak and c is equal to bl. But then if you substitute, so if you substitute the b here with ak, but then c is going to be equal to k times L times A. And so, of course, k times L is an integer. And so, by definition, by definition, A divides C, right? So here we use the definition that A divides B and B divides C means that there exists these K and L. And we need to show, we want to show that A divides C, so we need to find an integer such that that integer times A gives you C. And we know that there exists integers times A give you B, integers times, times B gives you C. And so if you do that replacement, you will find your integer KL that when you multiply by A gives you C. And so finally, the third one is that if A divides B and A divides C, then A divides any combination. So this is like a combination of B times something plus T times something, of course everything integers. So A has to divide every combination of this, right? So let's show this. So since A divides B and A divides C, that means that there exists, let's call them K1 and K2. So there exists K1 and K2 integers such that B is equal to A K1 and C is equal to A K2. But now, so therefore, when we write SB plus TC, we get, so B is equal to AK1, so it's going to be SAK1 plus TAK2. And so you can factor out the A here, and you get A SK1 plus TK2. And so that means that when you have SB plus TC, then there exists an integer that when you multiply by A gives you that. And that's exactly what we wanted to show. So thus A divides SB plus TC.